Well, thanks, Ken. As we all know, PQI is bringing together a diverse audience from physics, from chemistry, and engineering. So the goal of this talk is to show how quantum mechanics can inform the conceptual thinking in chemistry. When we think about quantum mechanics, we describe molecules in terms of wave functions, in terms of densities, expectation values, response functions, but that is not the way a classical chemist thinks about molecules, right? There's this notion of chemical intuition where there are atoms, and to each atom we assign a certain number of electrons, and once a certain shell is filled, we know the atom is happy. If there's a pair of atoms, they can share a number of electrons to form bonds, and then basically all of chemistry is about moving around electron bonds to form chemical reactions. Now, since we're in Pittsburgh, the goal of this talk is to show how can we bridge quantum mechanics and this notion of chemical intuition. One of the motivations of this is simply to gain more insights into chemical behavior. Here's one example that's pretty famous from the electrocatalytic reduction of CO2. CO2 is basically a waste molecule, but electrocatalytically it can be reduced to carbon monoxide, which is chemically more useful. But if we use a standard electroreduction, there's a large overpotential, which means that there's a large energy loss while performing this reaction. But if we perform it, for example, in an ionic liquid, then this overpotential is greatly reduced, and in other words, the energy loss is greatly reduced. So one question we naturally ask is, what is the intrinsic interaction between the carbon dioxide and the ionic liquid molecules to understand questions such as how and why does the ionic liquid facilitate the reduction of the CO2, and maybe we can even add a quantitative aspect to this notion of chemical intuition. Can we quantify how different types of ionic liquids would impact this reactivity? And the way we're going to probe this is we collaborate with a spectroscopist from our department, Sean Garrett-Rowe, to perform infrared spectroscopy, and we perform quantum chemical computations to unravel solvation dynamics of CO2 in ionic liquids, for example. Now, we all know if we want to extract information from quantum mechanical objects, we can use multiple tools, right? We can calculate expectation values, or if we want to investigate how a system responds to an external perturbation, we can use perturbation theory, or we can use static response theory or derivative theory to take the response of the system into account. Or if we have a time or frequency dependent perturbation, then we can use time dependent response theory. So there's a well-established toolbox for extracting information on observables from quantum mechanical wave functions and densities. But chemical intuition is based on quantities that are not observables in the quantum mechanical sense, right? We talk about atomic charges. Quantum mechanically, there's a finite but non-zero probability of finding an electron far away from the nucleus. So this notion of assigning an electron to a particular atom doesn't really work quantum mechanically. We talk about bond orders. There's no operator for calculating bond orders, right? Or there's no operator for describing charge transfer in quantum mechanics. So a central question is, how can we introduce a well-defined procedure to calculate such quantities from quantum mechanics? And clearly, there's no unique approach because there is not a single operator that we can define, but rather there's a plethora of approaches out there in the literature. I'd roughly like to categorize them either as perturbation approaches or as projector or localization approaches, and I say more about what they are. And as you can see, these are just the approaches that I'm more or less familiar with. Because there is no unique definition, people have come up with multiple different approaches. And I'll show you two basically extreme types. One is symmetry-adapted perturbation theory, which is probably the theoretically most well-founded and most well-defined approach. And then a more, let's say, intuitive approach, which is derived from these projector approaches. And I'll show you advantages and disadvantages of both in some applications. So symmetry-adapted perturbation theory is based on a simple idea. If we have a system consisting of two molecules A and B, then to zeroth order we write the wave function for the entire system as the direct product of the wave function for molecule A times molecule B. And we partition the Hamiltonian into different pieces. Most importantly, there's this part V that comprises all the terms that has electron-nuclear interactions between those two monomers. So V comprises all the intermonomer interactions, and then we can calculate meaningful interaction energies in terms of perturbation theory. For example, here to first order in this operator V, we would capture all the electrostatics between the unpolarized molecules. If we go up to second order, we allow the molecules to polarize, and we would then capture induction and dispersion effects. All of these terms are direct terms, which can be understood basically in terms of classical pictures. But we all know electrons are indistinguishable. The total wave function should be anti-symmetric. So actually, there are additional terms where we add an anti-symmetrization operator to this whole procedure, which then establishes a full anti-symmetry of the wave function. And this introduces additional terms that are exchange-like and which then do not have a classical analog, right? But these would introduce such important features such as Pauli repulsion. Now, this is probably a very well-defined, very accurate approach. On the other end of the scale, there's projector-type approaches. These are much simpler. One assumes that one can describe the systems reasonably well with an approach such as density functional theory, with its effective one-electron Hamiltonian, the Fock operator or Fock matrix. So for a system with two molecules A and B, there would be these diagonal blocks here for A and B, and this is the basis set representation of this operator. And then there are, of course, off-diagonal elements describing the spilling of the wave function from A into the basis set on the molecule B, and vice versa. The idea of these projector approaches is to successively decouple these off-diagonal elements. And one simple approach is simply to use a projection operator that basically projects out these off-diagonal basis set representations here in this Fock matrix. And I'd just like to emphasize, all that this means is that the wave function of monomer A is not allowed to use the basis of monomer B, and vice versa. The electrostatic and exchange type interactions are still embedded in the effective Hamiltonian. This just means that the wave function is not allowed to spill over from one monomer to another. And as a most extreme case, we would replace these diagonal monomer blocks with the unpolarized monomer wave functions, which I denote here with A0 and B0. So this gives us a hierarchy of different levels at which we can analyze the interactions between the monomers, right? At the lowest level, we have unpolarized monomers, but we do have electrostatics, charge penetration, and exchange type interactions between them. Then at this intermediate level, we allow the monomers to polarize. And then at the final level, we allow what this theory calls charge transfer. We allow the wave function of monomer A to spill into the basis of monomer B and vice versa. Now, clearly, this is a much more simple approach. And you might wonder, why would one introduce this if, if there's a very sound, well-founded, very systematic theory. And I can give you a practical reason. So these are the terms that occur in symmetry-adapted perturbation theory. This is all with Einstein sum convention. So if you see a repeated index, a summation is implied. For the direct terms, to calculate the interaction energy, things are relatively simple. I should notice this is probably the basic level of terms that one would want to keep. This is probably the minimum. But if we look at the exchange type terms, you can see there's a good number of these terms. And now let's consider, we are mostly interested in calculating molecular properties, so spectra, for example, and that would involve calculating derivatives of these energy terms. So if we have 5 energy terms, then the first derivative requires 25 terms. For the exchange, we get up to over 200 terms. So I think that makes it clear that while this is very appealing in terms of being very systematic, very accurate, and this is certainly the benchmark level that we want to compare to when we can, it is probably difficult to get higher order derivatives. Now let's contrast this to the projector type approach. As I said, this is just an SCF type approach, where the SCF type energy is just the trace over density matrix times some operators. If we take the first derivative, just look at this, we just get one additional term, and the reason is simply that we start out with a 0th order wave function that is SCF type, and according to Wigner's 2n+1 rule, in order to get up to first derivatives, we only need the 0th order wave function. So this is all that we need to get first order derivatives. So this is much easier. We get just one additional term as opposed to more than 200. On the downside, of course, the definition of what is called charge transfer in this type of approach is clearly going to depend to a certain degree on the local properties of the basis set, right? If we use different local basis functions, then we're going to get different numbers for this charge transfer. On the other hand, if we systematically and consistently use the same types of definitions of basis functions for different types of molecules, we're still going to get numbers that are going to be qualitatively transferable between different molecules. And so my group has applied this type of projector approach to calculate impacts of different types of intermolecular interactions on vibrational spectra. Here's just a very simple system to illustrate this. That's the water dimer. And we, as you can see, we can calculate the vibrational spectrum. In red, that would be the full normal spectrum that we'd get for the OH stretch vibrations. And with this kind of projector approach, we can switch off charge transfer. And you can directly see, we can directly measure the impact of this charge transfer on the vibrational spectrum, like a redshift of 100 wave numbers and the intensity increase. So this technique really allows us to decompose spectra into chemically intuitive contributions. And how we're really applying this to more complex systems, so we're working together with Sean Garrett-Rowe, also with Steve Corselli from Notre Dame, to really have infrared spectroscopy from the experimental side, electronic structure calculations to unravel the fundamental physics of the interactions, and then molecular dynamics to get the dynamical structure of the solvent shell. And I'd just like to give you a very brief teaser of what we found for this particular type of system. Basically, these are the vibrational frequencies of CO2 in different ionic liquids. And you can see there's a pretty clear distinction between them. What we found was what basically dominates the vibrational frequency is the CO2 structure in solvation. So you might think, okay, well, that's the end of the story. But with the projector technique, we can go deeper and ask, so what determines the solvation structure of CO2? And we found out that it's basically the charge transfer that determines this geometry, the impact of the geometry on the vibrational spectrum. Because if we turn off charge transfer, you can see there's basically no differentiation between the vibrational signatures in different ionic liquids. So in other words, we are able to correlate the vibrational shifts directly with the charge transfer. Now, if you want to learn more about the details of these applications, you have ample opportunity. My student Eric Bergquist is going to present a poster tonight, P7. If you want to learn more about the experimental side, you can go to Tom Brinzer's poster tonight. And actually, Sean Garrett-Rowe is going to talk more about the spectroscopy this afternoon. I hope I could give you a little teaser of that it is interesting and possible to bridge quantum mechanics and chemical intuition. And that's interesting because it adds a quantitative aspect to this chemical intuition, to those descriptors, and it also promotes the development of more insight into chemical processes. I briefly gave you this teaser about CO2 and ionic liquids, and I'd just like to mention there's a plethora of properties that are available, energetics, infrared, Raman, photoelectron spectra. Very recently, there's a pilot for nuclear magnetic resonance, so if you'd like to try any of this out, let me know. We're interested in this. I'd like to thank mostly Eric Bergquist for doing a great job, concerning also our undergraduates who are doing a lot of calculations on the ionic liquids. Thanks to everybody for your attention, and I'd like to open the floor for discussion now. Thanks.